So I am moving to something quite different, although I will use what we have said in the first lecture. First of all, let me define the set S of price vectors in RL such that P is strictly positive, by which I mean that all the coordinates are positive and the norm is equal to 1. The length is equal to 1. So that is the positive part of the unit sphere with center at the origin and the boundary being excluded. And I said already on Wednesday why it is convenient to normalize a price vector in this manner, but I will repeat it today. We are going to study one consumer at first, and a consumer for us is defined by, in this commodity space RL, plus by a preference relation which will be assumed to have properties which I will list in a moment, and an endowment vector, an initial endowment vector, which is a point in RL plus. You remember that RL plus is the closed positive orthant of the space. And the properties that I will assume on the preference relation are properties that you have seen before. With one exception, I will strengthen the convexity property. I have defined before a convex preference relation by the following property. If you take any point y in RL plus, the set of x that are at least as desired as y is a convex set. And I will strengthen this today in the following manner. I will assume that if we have two points, let us say indifferent points, y and y prime, indifferent to each other, then any convex combination of the two, that is any point of the straight line segment excluding the boundary points, that would be ty plus 1 minus ty prime, where t is strictly between 0 and 1. This point is assumed to be strictly preferred to y. So it's slightly stronger. It means that the boundary of this convex set contains no straight line segment. And by the way, why should we ever assume that a preference relation is convex? I think the best sign is simply this. If you take a budget constraint, that is to say, you have a price vector, and you consider the points Pz, the point z such as Pz is at most equal to W, and of course z belongs to RL plus, that is to say you face that consumer with a budget constraint, a price vector and a W given. That consumer will react by choosing a commodity vector which is the best according to his or her preferences in that set, and we do not expect that the consumer in question will be indifferent between two different demand vectors. If I observe your behavior given the price system and your W, you choose, apparently without hesitation, a given commodity vector. So that would exclude, certainly, a set which would have this shape, in which case you would indeed have two demand vectors. It also excludes the case in which you have a flat segment in the boundary, because you would be indifferent between all those points that would satisfy your budget constant. In any case, that is what we assume, strict convexity. So to summarize the properties of this preference relation, it is reflexive, transitive, complete. It has a closed graph. It is strictly convex. And we will even assume that it is monotone in a sense I have already presented in the last lecture. That is to say, if you have a given consumption vector, and if you increase, let us say, all the coordinates, then the point y is certainly preferred to the point x. You might be satiated with respect to one, with respect to many commodities, but you are not satiated with respect to all of them. And there is little controversy about this. So I don't give you the full list, but I repeat, not in writing, but strictly convex, monotone, closed, complete. And as for the endowment vector E, it's a point in RL+. This is very standard economic theory. So if we have the given endowment vector of that consumer here, and if we take a price vector P that belongs to S, I will want to exclude the boundary points for reasons which will become clear. Then the consumer in question will choose a certain vector here under those assumptions. It exists, it is unique, and we will call this G of P. So for a consumer with a given endowment vector, a given preference relation, there is a well-defined demand vector G of P. And the excess demand vector for this consumer is defined as F of P equal to G of P minus E. That would be this vector here. The vector G of P is in the boundary, is in the budget hyperplane because, for instance, of monotony. The function F has two fundamental properties under the assumptions I have given. One, F is continuous. That may seem obvious, but it is good to know that it follows from these properties. And two, as I have said already, G of P is in the budget hyperplane. That means that we have P dot G of P is equal to P dot G, dot for the inner product, and consequently P dot F of P is equal to 0, no matter what P is in S. So F is the individual excess demand function for this consumer. If we take an economy made up of a finite number of consumers, then the aggregate excess demand function is obtained by summing the individual F, and those two properties carry over in the summation process. So we could, in general, expect an excess demand function for an economy to satisfy the two properties. So you see there is a slight shift in the notation because I have reserved here so far F for the individual excess demand function, and now F will be the excess demand function for the economy as a whole, and F is continuous. And in addition, for every P in S, we have P dot F of P equals 0. That is not a different sign, so let me make sure there is no confusion. And that is the Walras law. So let me summarize. If we have an economy made up of consumers, all having preference relations with these properties, then the aggregate excess demand function for the economy will satisfy those two conditions. And the question arose, it was asked explicitly by Sonnenschein, and the year was, 1973 and before, whether those two properties completely characterize the excess demand function of an economy. In other words, given an F satisfying these two conditions, can you find a finite set of consumers, each one of them having a preference relation that is complete, transitive, reflexive, strictly convex, closed, monotone, and an endowment vector such that when you aggregate over those consumers, you can obtain in the end the given F. And Sonnenschein conjectured that the answer was yes, and he gave a first result along those lines. In 1974, Mantel proved the conjecture using differentiability for the function f, and proved that in fact such an f could be generated by an economy made up of 2L consumers, twice the number of commodities. And a little later, and that was shortly before my visit here in 1973, I proved the general result that does not assume differentiability, and the result also said that you could obtain that decomposition with L consumers. And since 1974, when this result was published, it has not been generalized. So it is probably safe to believe it won't be. And I intend to go, first of all, over the statement and over the sketch of the proof of this result, because I find it interesting as another justification of the normalization of the price vector by taking a Euclidean norm equal to 1. The usual rules apply. I welcome questions, interruptions if I have not been clear or if I have made an error. Walras law means that in the commodity price space, f of p is orthogonal to p. F now denotes the aggregate excess demand function. That is simply because the inner product is equal to 0. And that is a very powerful reason for normalizing p as I have done, because then if you have S here and P, then f of P can be represented as a vector tangent to the unit field. And the decomposition into L consumers was suggested by this geometric representation. The picture in R3 is much more convincing than in R2, and so I will present it. Suppose that P is here somewhere. You have a tangent plane, and you have f of P like this. And we are going to decompose f of P into a sum of 3 vectors, which will be obtained in the following manner. Let A1 be the unit vector on the first axis, A2 on the second, A3 on the first. If you project these vectors orthogonally onto the hyperplane, and don't forget that the vector OP is orthogonal to the hyperplane, so when you project, you obtain 3 vectors which will be shaped like this. Never mind the geometry. We can call them respectively B1 of P, B2 of P, and B3 of P. As I will show in a moment, one can always express a vector in the tangent hyperplane as a positive linear combination of those 3 vectors. When you are in a plane, in a 2-dimensional plane, of course, we all know that it is sufficient to have 2 linearly independent vectors, and you can express any vector in the plane as a linear combination of those 2. But if you want the coefficients in the linear combination to be positive or 0, then you must have at least 3 vectors. You cannot do it always with 2. And in this case, it works, and this is exactly how we are going to do it. So you see the proof of the result, which is not a trivial result if you look at the paper I published in 1974, is based on this very simple idea, which is strongly suggested by the normalization according to the unit Euclidean norm. If you have, I repeat, a vector which is tangent to the sphere, then taking the tangent plane, you can decompose this vector as a positive linear combination of the projections of the three unit coordinate vectors. Let me prove this. And first, let me draw again the unit sphere. So this is S in RL, and we want to eliminate the boundary and a part of S which is very close to the boundary. And the way in which we do that is simply to take a number epsilon, which is intended to be as small as you like, but strictly positive, and then we will denote by S epsilon the part of the sphere left when you have restricted for every I, pi to be greater than or equal to epsilon. Or greater than epsilon, it does not matter. So what you obtain in this case is a part of the sphere which is as close as you like to the boundary. And the result, the theorem, can indeed be phrased in this manner. If you have an excess demand function f satisfying continuity and Walras law, then for every epsilon positive, there are L consumers, all of them satisfying the strong properties I have listed earlier, such that the aggregate excess demand function that they generate is precisely f. So I have not written the theorem to save time. Is that clear to everybody? I will later on discuss the consequences of this statement, and they are, in a sense, quite devastating.
Can you explain why, if we go back to one consumer, we want the aggregate excess demand function to satisfy something like this, let's key restrictions, right?
Of course, I don't assume differentiability, so the Slutsky restriction would not even come in here.
Right, but if we had differentiability, to work backwards on the demand function for normal preference.
Yes.
You usually have to have some restrictions on the type of demand function.
If you have fewer consumers than there are commodities, then that gives you restrictions. But here, I start with an F, and I prove that you can perform this decomposition with L. In fact, there is an additional result that tells you that in general you cannot decompose with fewer consumers than L. So in that sense, it is the best result. But if you have fewer consumers than commodities, then there are results, and Erwin de Wert has worked along those lines, and two Soviet mathematicians, whose name I can give you later if you like. But in general, this is the best that you can obtain. So I repeat, if we have, and this apparently was somewhat annoying to econometricians in particular, who had always hoped that there were some restrictions on the aggregate excess demand function. And as we see here, aside from continuity and Walras law, there is in reality none, because you can construct an economy according to this theorem with L consumers that will generate the given F no matter what F is. You can perform this decomposition provided that the price vector stays away from the boundary. So you can have prices that are very small, but none of them can be zero. Let me go on with a sketch of this proof to convince you that at least the first step is easy and intuitive. So I go back to what I have said. Now I am more precise. I have a P in S epsilon, and I take the hyperplane through the origin that is orthogonal to P. I call it capital T of P. Of course, by a translation, it would become the tangent hyperplane to the sphere. As before, I denote by A sub I the unit coordinate vector on the ith axis. And if this is the ith coordinate axis, here is AI. And I denote by BI of P the orthogonal projection of AI into the hyperplane T of P. And now, given f of P, which is somewhere in this hyperplane, since P is strictly positive, we can certainly, by multiplying by a certain number theta, make this vector greater than or equal to 0. That is to say, f of P is somewhere here. By translating, as far as is necessary, you will eventually enter the non-negative orthot. And you can do that because P is strictly positive. Of course, if it were non-negative, it would not be possible to do that. And of all those numbers theta, I choose the smallest. That is when you just enter the closed positive orthot. You see the situation. You are somewhere in the hyperplane, and you follow P. You enter the non-negative orthot somewhere. That is theta 0. Theta 0 is a function of P which is continuous. That's fairly intuitive, and it can be proved indeed. So to remind you that this depends on P, I will write theta 0 of P, strictly positive, which is continuous. And now I take a function theta of P that is continuous and that is strictly greater than theta 0 of P. And if theta 0 of P has those simple properties, it's a continuous real valued function of P, then surely you can find easily a theta doing that. And now that you have done that, you have f of P plus theta of P, a vector that has all times P, a vector that has all its coordinates strictly positive. Therefore, you can write it as the sum with the coordinate vectors AI, and I will write the coordinates, let us say, beta I of P. And all those numbers beta I are continuous functions of P, and they are strictly positive. And if now you project this vector into the hyperplane, since P is orthogonal to the hyperplane, you obtain by projection 0 here. F of P is in the hyperplane, it is not disturbed, and you find that this is, when I varies from 1 to L, beta I of P times bi of P. Sorry, I have used a superscript. So that is the kind of mistake that you are supposed to catch me about when I replace a superscript by a subscript. So there you are. We have done exactly what we wanted. We have written f of P as a sum from 1 to L of those projections of the unit vectors multiplied by beta I of P, all of them strictly positive and continuous. And now there remains only to show that each one of these can be expressed as the individual excess demand function of a consumer having all the required properties. And that is how you perform the decomposition. And that is the difficult part, and I am not going to do it. So does it make sense? The result in question has three main consequences. All of them worth knowing. The first I have already mentioned. There are basically no restrictions on the aggregate excess demand function of an economy. So this is for econometricians to worry about. The second, and I will elaborate this in the second part of this lecture when I talk about existence of an equilibrium, by using this result, one can prove that the existence of a competitive equilibrium implies a fixed point theorem. We already knew, of course, in the other direction, that a fixed point theorem gives you the existence of a competitive equilibrium, and it has happened repeatedly in the history of mathematical economics and of mathematics that a result was proved with excessively strong assumptions. Consequently, one inevitably was to ask whether one could prove the existence of a competitive equilibrium with tools, mathematical tools, less powerful than fixed point theorems. And the answer, because of this result, as I will make very clear later, is that one cannot do it. So it's very comforting. At least we can believe that we have an optimal proof of existence. The third consequence is also very disturbing. If you look at the theory, dynamic theory of economic equilibrium, you may remember that when Arrow and Hurwitz wrote their paper on stability of economic systems in Econometrica, they conjectured, they said that they had never met a system that was not stable according to the Tatton-Moore process. And therefore, they more or less conjectured, I don't remember the exact wording, so you have to be careful, that every economic system was stable globally according to the Tatton-Moore process. That was a challenge, a glove that was thrown into the face of theorists, and Scarf came shortly thereafter with an example showing that an economy could be unstable, globally unstable. And this result carries the argument to its extreme conclusion, because if you check a dynamic economic system and the Tatton-Moore process, here is P, here is aggregate excess demand. If you take dP over dt, that is, let us say, proportional to f of p, it means that you have a dynamical system on the positive part of the unit sphere. And the behavior of that dynamical system will be entirely determined by the function f. Now, what this theorem tells you is that the function f is completely arbitrary. So, in other words, if you give me any dynamic behavior, unstable if you like, or stable, any dynamic behavior, then I can construct an economy, thanks to the theorem, that will give you exactly that Tatton-Moore process behavior. So one could reverse the conjecture of Arrow and Hurwitz and say that essentially economies can be as unstable as you like if you take this viewpoint. I don't quite believe, of course, in the Tatton-Moore process as an accurate description of what goes on in reality. So I intend to come back and to clarify the statement I have made, statement number 2, but on the other 2 points I don't intend to say more unless there are questions. One can make the result even stronger. That was done in particular by Kerman and Koch. In the Review of Economic Studies 1986, they showed that you can obtain the result I gave you even if you restrict all the consumers to have the same preference relations and all their initial endowments to be not only collinear, but in fact to have an a priori given wealth distributions. So if you give yourself, you have L consumers, if you give yourself numbers, which they call probably mu1, mu2, L. They are all non-negative. They add up to 1. Then you can choose your endowment vectors to be collinear and to be spread on the half-line from the origin according to the lengths nu1, u2, un. So you can specify the expenditure distribution in advance. You can require all the consumers to have the same preference relations, and you still get the decomposition into L. So you can present this theorem in the most devastating possible way, since you can add all those restrictions. So that is the characterization of aggregate excess demands in the general case. And in a sense, it was a cause for sadness among economists, but it...
When you wrote the aggregate excess demand function as a positive linear combination of the projections of the price vector on this plane, are you saying that each of the, I'm just trying to intuition, the price of changing the plane is going to change around, and so you're saying each of those components, the FIP.
Let me draw a picture for two consumers and see whether it clarifies the question. The case of two consumers, two commodities, is quite trivial, but nevertheless, it may indeed clarify this matter. Here we are. Commodities 1 and 2, and for any price vector P, we have somewhere on this tangent line an excess demand vector, and here is A1, and here is A2.
What is the Euclidean norm?
1 is the Euclidean norm, yes.
Why?
Oh, I have chosen it that way simply because by restricting P to be on the unit sphere, then Walras law, P dot f of P equals 0, tells me that f of P is tangent to the sphere.
Some of the squares of the price of the commodity and some
That's
of the
right. It's completely arbitrary. It's a mathematical artifact, but it has the great convenience of giving you the excess demand vector as a vector field on the unit sphere. And it works beautifully. You see, you can normalize the price vector as you like. The length of the price vector is totally, in this context, irrelevant. As I said on Wednesday, you can measure prices in dollars or in cents. That is to say, you can multiply every price by 100 if you like. It does not make any difference.
linear space, of course.
Yes, in a linear space. The commodity space.
The Euclidean space.
Well, the Euclidean space is.
The Euclidean example.
Yes.
Very trivial example, very special.
But there is no objection to this normalization.
No objection to it.
No. I don't pretend that this normalization has a particular economic meaning, but we could normalize the price vector in any way we like, and I can think of 3 normalizations that have been used. One of them, the oldest and the most common, consists of choosing one commodity and taking it as a numeraire. So you take the price of 1 unit of that commodity to be 1. It could be an ounce of gold. If you do that, it means the normalization brings the price vector to be anywhere in this hyperplane orthogonal to the first coordinate axis. So if you have a price given like this, then you can take the normalized price vector, if that is the numeraire. There is one objection to this normalization. It will work very well unless the price of the first commodity is 0. And if you take a very broad viewpoint, you have to explain why in an economic system some commodities have a price 0. You cannot take this as an assumption, as a given. And it used to be the case that water in the 19th century was considered to be a free good with a 0 price. But we take a stricter viewpoint. We want an explanation of which commodities have a zero price, and we are absolutely right, because fresh water is no longer that free commodity that our ancestors used to have. So a free commodity would be an outcome of the technology, of the resources, of the tests of the particular economic system. For that reason that normalization is not favored by economists, then sometimes they normalize the price vector by restricting it to belong to the unit simplex of the space. That is to say, you take either the straight line segment connecting the 2 points at unit distance from the origin, you take an equilateral triangle in R3, etc. Why does one like this normalization? Because it gives you a set which is convex. That's very nice. The surface of the unit sphere is not convex, of course, but topologically equivalent. All those normalizations are, from our viewpoint, acceptable, this one being the least satisfactory because of the reason I have said. But otherwise, take the normalization here as a convenient mathematical artifact. And there can be no objection to that, since you can prove with it the result that I have said. If you forget about S, you can formulate the theorem I have given you without any reference to Euclidean norm. It would still be true. You would have Walras law, of course. So going back to your question, we have the aggregate excess demand vector here as tangent, and the projection of A1 on the hyperplane in question. I can draw the parallel hyperplane, which in this case is a straight line. Of course, the orthogonal projection is here. So here is B1 of P, and here we have B2 of P. And as you see, any vector here can be represented as a positive linear combination of these two. In this particular case, it would be a positive linear combination of B2 of P only. If f of P were pointing that way, you could represent it as a positive linear combination of B1 of P, or possibly as a sum of the two. And once you have done that, then here you can easily show that there is a consumer having, don't forget we have to multiply by beta 1 of P, so we have a collinear vector like this. That would be B1 of P multiplied by beta 1 of P. And you can easily construct a consumer who has this as an individual excess demand function. Choosing an E anywhere here, you can construct a preference field. And similarly for the second consumer. Those are very special, but they are sufficient.
If you were willing to assume differentiability,
Yeah.
then each of those components f by p would satisfy the question equation.
Yes. Yes. Now, any question? I try to answer them very fully, since I have said I would welcome questions. If I have not answered fully, press me and I will give a fuller answer. But if this is sufficiently convincing, it's a very special case indeed, but it may persuade you that everything is all right. And the complete proof is in the Journal of Mathematical Economics, 1974. So what was the next step? It became perfectly clear after this negative result that if one wants to have interesting properties of the aggregate excess demand, one must assume something about the distribution of tests and of resources in the economy. We could do that because they are arbitrary. And I will mention one result which I find especially interesting. No proof, of course, given by Werner Hildenbrand in Econometrica 1983. It is mentioned in the list of references here on the law of demand. So we have for each consumer an endowment vector, and a preference relation. It is naturally very hard to say anything about the distribution of preference relations, because a preference relation is an element of an infinite dimensional space. It is much easier to talk about the distribution of E, because those are points in RL+, a finite dimensional Euclidean space. I will take a slightly different notation, so forget what I have said before. If we have a given price vector and a number, real number W, therefore the budget constraint would be Px smaller than or equal to W, I denote by F the demand for that particular individual given P and W. All the individuals are faced with the same price vector. We are going to make an assumption about the distribution of expenditures. And we know perfectly well that in any economy, in our economy, expenditures are not arbitrarily distributed. If you give me a distribution of expenditures which is shaped like this, I won't believe it, and none of you will believe it. Distributions are not arbitrary. They are in fact extremely restricted, as I will say later. And here is the result of Hildenbrand, which was remarkable in several ways. We assume, as I have said, that all the consumers have the same demand function. Or that is, in a sense, outrageous, but you might say later that the assumption I will make on the distribution is conditional on the demand function. And we only assume that this demand function satisfies the weak axiom of revealed preferences. Now, the individuals composing this economy will be assumed to form a continuum, and there is no objection per se, because when you see a curve representing a distribution of expenditures, of income, of wealth in an economy, you see it never as, if you have 100 million households, as a staircase, but as a continuous curve. So econometricians have no qualms, and nobody should have qualms about assuming that consumers form a continuum for the purpose of statistical description. So we assume that W is distributed over a continuum of consumers, and that we have, for this distribution, a density, O, which has a finite mean. The strong assumption that we are going to make, following Hildenbrand, is that the density is non-increasing. I will have more to say about that. So it means that if you take the distribution of density, it may be something like that. Otherwise, absolutely arbitrary. And with these properties, if we denote the aggregate demand for the entire economy, which is now a function of P only, and it will be equal to the sum, the integral PW rho of W dW, and you integrate over the real line, then this aggregate demand will have the strong property of monotony. And this is what I meant in the description of this lecture which I gave you. I say that the distribution of expenditures is monotone if the density is non-increasing. And I say that the aggregate demand function for the economy is monotone if the following is true: for all pairs of price vectors P and Q, you have f of Q minus f of P, vector in RL, inner product Q minus P, smaller than or equal to 0. And this is Hildenbrand's first result. It is remarkable because the person in the street believes that if you increase the price of a commodity, then the aggregate demand for that commodity will decrease. And economists until 1983, as far as I can tell, we are never able to prove theoretically this result with any reasonable assumptions. And there, of course, you have it, in fact, in a stronger form. Because if you vary only one coordinate of the price vector, let us say of the first commodity, all the other coordinates being 0, then that tells you, of course, that if you increase P1 to Q1 greater than P1, then it tells you that F1 of Q will be smaller than or equal to F1 of P. This is a much stronger result. And at last we have a justification, theoretical justification for this. So I repeat, we take an economy made up of a continuum of consumers. They all have the same demand function, which is only assumed to satisfy the weak axiom of revealed preference. And of course, if the consumer has a preference relation of the type I discussed half an hour ago, this is certainly true. Then, assuming that the density of the distribution of expenditures is non-increasing, the aggregate demand will have this strong monotony property. If you make it just a little stronger, if you have here strictly negative when the two vectors are not collinear with each other, then this means that there will be a unique equilibrium. It's a very strong property. And if you don't like the assumption that they all have the same demand function, we only ask that conditional on the demand function, the distribution of expenditures has a monotone density. I have no intention of going through the proof, not even through the proof in the monotone case, although it is extremely interesting because you can derive the proof in the case in which f is differentiable. Now we are going to use implicitly the Slutsky relations. The fact that f is monotone would be expressed by the fact that the Jacobian of f is semi-definite negative. And you can easily derive that in 5 lines from the Slutsky relation. And as a point of methodology, it is interesting to me that economists by the tens of thousands have seen the Slutsky equations and could have made this derivation that Hildenbrand did. Nobody did it. And my point is that if you don't have a research program, you cannot blindly, by groping in the dark, find even a jewel lying in front of you. But as soon as you are directed by a goal to attain, then it becomes far easier. And the filiation of ideas in this area, as I see it, is precisely the effort to characterize fully the aggregate excess demand function of an economy, this gloomy result that any function satisfying continuity in Walras law could be the aggregate excess demand of an economy, then the desire to circumvent this negative result, make assumptions about the distribution of preferences and resources, and the simplest was to assume the same preferences because it is difficult to say anything about distribution of preferences, and then, lo and behold, you have this result, which was the first theoretical justification of the law of demand in a strong form. Is that reasonably clear? Yes.
In the Hildenbrand result, are the x's strictly quantitative or are we on to clients as well?
Here, of course. Well, you have, if you want to have the stronger result to which I alluded, namely negative if P and Q are not collinear, you have to make a slightly stronger assumption. But that is not perhaps an important point. And it is fully clarified in Hildenbrand's paper, of which I do have a reprint here, but it is in econometrica, so it is available to everybody. Now, that result is not the end of the story, obviously, because the density of the distribution of expenditures is not decreasing. If you look at the standard distribution of income curve, it will look, let us say, something like this. The log normal has often been proposed, and so you have a decreasing density in that range. but not in this range. But several comments are in order. First of all, this range is, of course, far larger than this one. And remember that when I assumed decreasing density, actually it could be decreasing as little as you liked. So a density even constant for an interval like this. Well, this means that we have here a lot of room to spare, because you have here a sharply decreasing density, and to obtain this result you need only a non-decreasing density. But this part of the range is bothering, and it has led Hildenbrand to study empirical data. It's a remarkable example of very pure theories becoming very applied, and that is one of the references I gave in this list of references. But the book, having been published last summer, is not yet available here. What I propose to do is to leave in Christchurch a Xerox copy of this chapter, if you want to look at the paper, which is entitled On the Mean Income Effect, a Data Analysis of the UK Family Expenditure Survey. Well, this is very much the research is very much in progress. I think it's an extremely interesting area of research. Namely, the goal is to formulate assumptions on the distribution of expenditure, distribution of taste, if one can, so as to obtain strong properties of the aggregate demand function, which is certainly what we want. And we know that from a theoretical viewpoint, if you don't make those assumptions about the distribution, you can get any aggregate excess demand function that you like. It's a good time for the break. After the break, I will talk about existence of an equilibrium, no proofs, but I will discuss the formulation, the result, the approaches. So if you have questions about this first topic, now is a good time to ask them.
One question on the endowment. Is it essential that all commodities in the endowment, in fact, enter the utility function?
Let me think. No, not really, because we have assumed that the preference relation is defined on RL plus, boundary included, and all the assumptions I have given do not exclude that you have points on the boundary, for which, therefore, you would have zero consumption. So you may very well have a demand, which is, for example, here. We have excluded some prices being zero. But that, of course, would be excluded if you have a monotone preference relation. As soon as you know that by increasing coordinates of the commodity vector, you increase preferences, then no price can be zero, because that would lead to an infinite demand, no equilibrium. So it's quite possible to have an equilibrium on the boundary, on the space. The result I have mentioned has been extended in the case of differentiability in the book by Mas-Coley. Then you can make a statement about the indices associated with the aggregate excess demand function. Now, on existence, I want to do, first of all, I want to remind you of the description of an economy that Hero and I proposed some time ago to discuss the assumptions required to obtain existence and see which ones are acceptable, which ones are not, what kind of work is being done. I want to discuss the various approaches to the existence problem, and if time permits, tell you still other things. And as you have seen, according to the description of the lectures I gave you, I intend after that to discuss generic local uniqueness, then the theory of the core, and at the end of my last lecture, I want to discuss another exciting area of research, which is at the borderline between economic theory, mathematical programming, and the theory of games. I suspect I won't have much time to talk about that, but at least I can refer you to a few papers, some of them unpublished, of which I will leave copies here. So the economy we are discussing is the following, possibly well known to all of you. We have a number of consumers, I, running from 1 to m, and for each one of them a consumption set that is a non-empty subset of the commodity space. That is to say, the consumption small xi of a consumer must be an element of this a priori given set. And where does it come from? It can be determined by the fact that if you actually consume a commodity, the quantity of that commodity has to be non-negative. If you produce a type of labor, the quantity of that labor you can produce as an upper bound, etc. So there are various bounds given a priori that determine the set capital Xi that we don't try to explain. It is the consumption set of the i's consumer. And on this set we have a preference relation of the type we have discussed at great length in the first lecture. And finally, each one of these consumers has an endowment vector that is a point EI in RL. What do we assume about the preference relation? At this stage, only that it is reflexive, complete, and transitive. We will make more assumptions later. So that is for each consumer the way things look. Then we have, so all this, I runs from 1 to m, and then we have producers, and each one of them, let us say the j's, has a given set of possible production vectors, that is to say input-output vectors. You specify for a producer the inputs and the outputs, you get a vector, and the question is this vector possible or not? That depends certainly on the state of the technology, among other things. And the last thing that you need is to specify how the profits of the producers are distributed to the consumers. So Yj again is non-empty and is a subset of the commodity space. So theta ij means the share of the profit of the j's consumer that goes, of the j's producer that goes to the i's consumer. And those numbers are non-negative, and they must be such that the sum over I of the theta ij is equal to 1. That is to say, the profits of a producer are fully distributed to the consumer. And given an economy of this type, which, as I have said, I assume to be known to almost everybody, we want to explain how the various agents will eventually decide to behave and what the price vector corresponding to this situation will be. So we want to explain for each consumer the consumption vector xi, for each producer the production vector yj, and the price vector p. These various vectors belong to RL, and we have an equilibrium, which I will denote by a star, if the following is true. Well, first of all, xi star must satisfy the following condition. If the price vector is p star, then the i's consumer has the following income or wealth, according to your interpretation of the commodities. Summation theta ij P star Yj star. Yj star being the production vector chosen by the jth producer. Then the profit of the jth producer is this number, and the share going to the ith consumer would be theta ij. If you sum over all producers, this is it. And so the ith consumer must satisfy this budget inequality, and xi star must be best for his preferences under this constraint. So that is the first condition. In order for the ith consumer to be in equilibrium, xi star must be the best for his preferences under the budget constraint that we have here. For the jth producer, Yj star must maximize profit, or that must be the maximum of P star dot Yj when Y sub j belongs to capital J. Given the price vector, the producer must satisfy this equality. And finally, you must have equality of demand and supply, which can be written as this equals 0. So there you have the economy and the condition for equilibrium. Now, what assumptions must you make? And that is the first point I want to discuss. What assumptions must you make on the economy in order to be sure that there is at least one equilibrium of this time? I am going to list them and tell you those I consider to be quite acceptable and those that I consider to be bothersome. So for every I, xi is assumed to be closed, convex, and bounded below in the sense of the coordinate-wise ordering of vectors. So that is to say, in RL, whatever xi may be, let us say a set like this, we simply assume that there is somewhere a vector so that if you translate the positive orthant far enough down to the left, the translate will contain xi. That is what bounded below means. We assume that there is no satiation in xi. You can actually restrict xi to a subset. We assume that the preference relation is closed, convex, in the sense that if you take two consumption vectors, xi and xi prime, if xi prime is strictly preferred to xi, then all the points of this segment, such as x double prime I, are also preferred to xi. Of course, you must exclude xi itself. Well, that is a variant of the convexity assumption that I gave you earlier. We assume that there is an xi 0 in xi such that xi 0 is strictly smaller than ei, and then for every producer you assume that the set Yj contains the origin. You assume that Y, the total production set, which is the vector sum of the Yj, is closed and convex. You assume that you have what is described by irreversibility. That is to say, if you take the set Y and let us say something like this, and the symmetric with respect to the origin, which would be like that, their intersection is 0. And finally, you assume that Y contains RL minus. RL minus being this. So you would have, here of course the set would not be, let me redraw it to make it convex. So it would, like this, it would contain it. I think my list of assumptions is complete. You have probably seen them before, but what I want to do is to go over the list and to see how strong they are. The assumption of closedness is perfectly tolerable since it cannot be disproved. You cannot distinguish practically a set from its closure. We are talking about quantities that are as small as you like. Bounded below is very acceptable since for a commodity that is actually consumed, the lower bound would be 0, and for a quantity of labor, which would be a negative coordinate here, you have an upper bound on the quantity of labor that can be produced in a given time interval by an individual. Convexity, I will come back to this when I discuss the convexity of preferences. Here, no satiation in Xi, that is a fact of everyday observation, excluding possibly a small set of assets. If you take any individual in this room, I am quite sure that no matter what his or her consumption is, there is another one that that person prefers. The closedness of the preference relation, the same comment could be made as before. Convexity, I will discuss together. Now we need this assumption to make sure that for a given price vector, any price vector, the individual will not be left, once the budget constraint operates, with a literal impossibility in the choice of its consumption vector. And that is indeed one of the strong assumptions. That the origin belongs to Yj means that the producer has the possibility of having no input and no output. And Y closed is not damaging, convex is something I want to discuss. Irreversibility is indeed very acceptable. It can be weakened. In fact, it simply means that I will take a striking image to make it clear. If you take the Chicago stockyards, you cannot put sausage meat at one end and get a live pig at the other. Yes? But you can make it even stronger because those commodities being dated, irreversibility would also mean a reversion of time, which certainly is not within the realm of possibilities. And that is free disposal. That is to say, if you have only inputs and no outputs, that is feasible. There are objections to that because, as we well know, it is not always costless to dispose of certain residuals, such as nuclear reactor residuals. But that assumption can be weakened very much. I think we are left as strong assumptions with convexity assumptions and with assumption I have underlined. And in the case of convexity here, for consumers, that assumption can be dispensed with completely, as we have learned from Oman's paper. If you have an atomless measure space of agents, then convexity is irrelevant. You inevitably get convexity in the aggregate because of Lyapunov theorem. So there remains convexity for the aggregate production set, and that is a very real problem. It does exclude increasing returns to scale, but notice that this assumption is made only about the total production set. The individual production sets might not be convex, but you require this. So to my mind, the most damaging assumptions, possibly the only damaging assumptions, are the one I have underlined here and the convexity of the aggregate production set. Having said this, and unless you wish me to explain or you wish to contradict, I will go on to various approaches to the problem of existence, which are interesting in their own right for various reasons. So here it is. This model has been extended in the recent past in many directions, and I will list some of them at the end of the lecture. Let me now talk about approaches to the existence problem, unless you wish to discuss this further. I am giving you the model as it was formulated several decades ago by Gerard and myself. It has been extended in a number of ways, but I wanted to tell you what, as of now, can be considered the weak or the strong assumptions. And what we have learned from the introduction of large economies in the sense of Aumann and his followers is that convexity for consumers could be dispensed with completely. Oh, this is the strong assumption, as you would expect. And this one. There are by now many ways to prove an existence result for an economy of this type. And the first approach I will discuss is in fact the approach that Gerard and I used, and I thought that it was going to be displaced by another approach I will present later, but it has come back into its own for reasons which I will try to explain. Let me go one step higher in the degree of abstraction and describe what I mean by a social system. And I will say how a social system is a generalization of the economy of the type we have discussed before. It is also a generalization of the concept of a game. We assume that we have a number of agents in the social system, let us say M of them. The notation, of course, is quite different from what you have seen before, and each one of them has an a priori given set of possible actions. In the case of a game, it would be the set of strategies. In the case of a consumer, as you will see earlier, AI would be capital Xi, and an action would be a small xi in capital Xi. So we have an AI for each one of them. Then, symbolically, here they are, A1, A2, AM. Once the actions of all the agents except the I's have been chosen, that is to say A1, A2, AI minus 1 and AI plus 1 to AN, When the actions of the others have been chosen, the action of the I's agent is restricted. That is to say, the other people in your social system restrict your freedom of action. We will use that in applying this general result to the economy of the preceding time. So if you take here separately the set AI, given all these actions, you are now restricted to a subset of AI, which we are going to call phi I of, and I will say A. And by A, I mean the entire list of actions. And it may seem bizarre to include the action of the agent itself, but formally it is a simplification. We simply require that phi I does not depend on A sub I. So it's a function with a sort of dummy variable. But we have this. So for every I, we have this correspondence which defines a non-empty subset of AI given the actions of the others. And the only thing that we have left to specify is if the social state is A, simply a list of all the actions chosen by the agents, then the utility to the I's agent is Fi of A. We have different utility functions for the different consumers, and we specify that your utility depends not only on what you do, but on what the others do. And it is indeed the case. Now, we will have an equilibrium, which I will denote by A star, if and only if the following is true. Take the ith agent is restricted to phi I of A star, and of course this can be written as A sub M, the set of all the agents, minus I and AI. That is to say, in the list of all the A's, I have selected here the list of the actions other than the I's and the AI. You have no control over what the other agents do, and therefore on this set phi I of A star you maximize with respect to AI. So it should be the case that Fi of A star is the maximum when AI belongs to phi I of A star of Fi of A M minus I star and AI. That is the equilibrium condition. Now, what are the assumptions that you make on the various objects here in order to obtain existence? You assume that all the AI are convex, compact, and not empty. You assume that phi I is convex valued, and remember that it is defined from A, which is the Cartesian product of the AI. So phi I is defined on A and takes its values in AI. It associates with every element of capital A a non-empty subset of AI, which is assumed to be convex, and you assume that phi I is continuous in the sense of continuity of correspondences. And finally, Fi, the utility of the ith agent, is assumed to be continuous in A and quasi-concave as any standard utility function is in AI. So in the variable AI. And with these conditions, you can obtain existence. The proof is absolutely transparent. And this is how it works. We take the set AI, given the actions of the others, this agent is restricted to phi I of A star, and within this set, the agent considers its utility function. Those are the actions of the others. This is his own action. He's going to maximize Fi with respect to AI, and that will give a subset of phi I of A star, which I call mu I of A star. And to say that you have an equilibrium for this agent is to say that AI star belongs to mu I of A star. This must be true for every I. And consequently, this can be expressed in the following manner. The point A star, which is the list of A1 star, A2 star, etc., must belong to the Cartesian product from 1 to m of mu I of A star. And this can be symbolically represented as follows. Suppose that you have only two agents, and if you had m, the symbolism would be the same. If you have an arbitrary state of the social system represented by A, therefore A1 and A2 are here, you see A2 determines the set phi I of A to which this agent is restricted. And then within that set, the subset mu, which I will represent here, mu 1 of A m minus 1. And similarly here, given A1, you would have mu 2 of A m minus 2. And the Cartesian product I have written here is the Cartesian product of those two sets. So here it is. And you do have an equilibrium if and only if this point belongs to this set. So that presents an equilibrium as a fixed point for a correspondence defined on capital A, the Cartesian product of all the A sub I. And this is a picture that we presumably will never forget once we have seen it. And it is already a convincing argument in favor of using a fixed point in problems of existence of an equilibrium. So you see what I have done. I have taken the set of actions of each agent, A1, A2, and you could add A3, A4, etc. And we consider an arbitrary state of the social system, A. The optimal reaction of the first agent to this state consists of taking A1 in that subset, which has been defined here. Similarly for the second. And you have an equilibrium if and only if each agent is fully adapted to the actions of the other, which means that small a belongs to this set which I have called U of A. So the name of the game is simply to make assumptions on the data such that this situation is covered by Kakutani's fixed point theorem, which it will be in the cases I have described. So assuming this is more or less familiar to all of you, and assuming that for those who are not familiar with this, this presentation has at least some intuitive content, this is the basis for proofs of existence using Kakutani's theorem. How does one reconcile this general social system with the economy I described earlier? Very easily. This is how you proceed. The various sets A1 to, let us say, A capital N are the following. First of all, you have the consumers. So the set AI for each one of them is the set capital Xi. So here to Xn. For the producers, the sets are Y1, Yn. And then you have the price setting agent, a pure fiction. Once again, we are after a mathematical proof. If we normalize the price vector in such a way that prices are restricted to the fundamental simplex of the space, that is to say, all the prices are greater than or equal to 0, and the sum of their coordinates is equal to 1, let me call phi the simplex. How then is the payoff for each one of these agents defined? For the first agent, the utility function is U1, which is a representation of his preferences, as we said in the first lecture. Similarly, Um, a representation of the nth preference relation. The payoff for the first consumer is simply, given an element P in capital P dot Y1. So you see the payoff here depends on his own action, Y1, and on the action of the price setter. And similarly here, Pyn. Now you have to define the payoff to the price setting agent, and that is apparently artificial, although it has some economic content. Suppose that the first agent has chosen X1, the nth Xm, the first producer Y1, Yn. Then when all those agents have made those choices, there results for the economy an aggregate excess demand, which is the summation of the xi minus the summation over j of the yj minus the summation over I of the ei. Call this vector z. What is the role of a good price setter, of a price board? It is to reduce this aggregate excess demand, to drive it to zero somehow by a wise choice of prices. And one way of embodying this idea in this context is to choose for the price setter the following payoff. That is to say, Z is given, and you choose P so as to maximize the value of the aggregate excess demand. It's a pure mathematical concept, but it does make economic sense, because if you have a commodity for which the excess demand is large, then you would want the price of that commodity to be large, because you want to decrease that aggregate excess demand, and vice versa. If you have a large aggregate excess supply, you will make the price of that commodity low. And this is what is reflected by the choice of this payoff. But its justification is simply that if you take that payoff, then the entire economy that I have described earlier is a particular case of a social system of this type. And therefore you can apply this argument and prove the result like this. That is what Hero and I did, and as I have said, later on, a different approach, of which I will talk now, became more popular, but recent work of a number of people, including Mascoley, Gale, Schaefer, Sonnenschein, has shown that this approach, after all, could be more appealing because it leads to greater generality. I will come back to this point. The second approach I want to discuss is precisely the approach that seemed fated to replace this one, and I will call it the excess demand approach. And this is a mathematical formalization of very classical economic ideas. So I told you at the beginning of the first lecture that one drawback of my enthusiasm about lecturing here would be that I would cover a lot of ground, possibly too much. But I am comforted by one comment that von Neumann used to make, that it was not necessary to understand everything in a lecture to derive some benefit from it. And indeed, if you understand everything, I would say the lecture was quite superfluous. The other approach, the excess demand approach, is as follows. Suppose in the economy that I have described that you give yourself an arbitrary price system. Then producers will choose their production, consumers their consumption, and there will result altogether an excess demand vector, which I will write here. Let us say Z. That is a result of the choice of the price vector P. The price vector P may not determine Z uniquely. Therefore, we expect to find here a set of points, phi of P. It is easy to obtain a uniquely determined reaction of a consumer by making the preference relation strictly convex. And I gave some arguments in favor of uniqueness of demand. Unfortunately, we want to be able to include in our theory the case of industries working under constant returns to scale. And there we cannot help the fact that a given price vector will give rise to an infinity of optimal input-output vectors if we have constant returns to scale. That is the justification for working with correspondences. That is to say, phi of p, a non-empty subset of the commodity space, but in general containing more than one point. And this is the excess demand approach. Here is the price vector p, which will be normalized eventually in some way. Here is the orthogonal hyperplane. There results a set phi of p. I will specify the assumptions that phi of p has to satisfy, and we will have an equilibrium if the set phi of p has a non-empty intersection with RL minus, which I have shaded here. A non-empty intersection means that you have an excess demand vector that is negative or zero in all its coordinates. So it is conceivable that on some markets you have a zero excess demand, and on others you have a supply that exceeds demand. It's acceptable. In that case, of course, the price should be zero for that commodity. But that is not excluded a priori. So that is what we are looking for, a P that will lead to this relationship. And if you make the following assumptions on phi, it is possible to show that there is a P, let us say, in the set capital P that I have defined earlier, that will satisfy this relation. Phi has to be what we say in our jargon, upper hemi-continuous. It means that this correspondence has a closed graph, essentially. What I say is not quite true, but almost true. So phi is upper hemi-continuous. Phi is convex valued, which means that for every p, the set phi of p is convex. And you can see how this would be derived from what we have said earlier, because the reaction set of every agent is a convex subset. For a consumer, it is possibly a single point, or in any case, if it is not a single point, because you have not assumed strict convexity of the preference relation, since the preferred or indifferent sets are convex, the intersection set here is going to be convex. And similarly for producers, if you assume convexity, say of capital Y, then the corresponding set of optimal reactions is going to be convex. And phi of p is obtained by making the vector sum of all those convex sets. It is convex. Or if you have a measure space of economic agents, you obtain convexity in the aggregate in any case without making any convexity assumptions on the individual characteristics. And finally, for every p, you assume that p dot f of p is smaller than or equal to 0, which means that the set phi of p is in this closed half space below the hyperplane. This is simply derived from budget constraint and similar observations. And if those conditions are satisfied, then you can prove, and that was proved by Gail, Nikaido, myself separately, that there is a point, P star, at least one, for which you have this relation. So there is at least one P star in capital P for which this set will intersect this one. Intuitively, you can see why it has to be that way. Here is capital P, and small p is a point here. Now, suppose that you go from one end to the other of capital P. You start here. The orthogonal hyperplane is here, and phi of p associated with this price vector is somewhere here. If that set intersects, well, you have an equilibrium. If it does not, it will be, let us say, like that. As you start moving this way, in this situation, then here it is. That set which has to remain below the hyperplane is going to be here. And as you see, as you move towards this point, the set is going to be squeezed against this straight line. It can escape only if it could go to infinity, but it can't because of boundedness. So at some point, either you are going to cross here, and therefore this set will include the origin, or you will be squeezed against the boundary here, and have a situation like this. Here is the plane, and your set will be something like that. So that's very intuitive, and it works beautifully for dimension 2. Of course, for higher dimensions, it's a little more tricky, but true anyway. So does that make sense? It's very classical. You have for every price vector an excess demand due to that price vector, which may not be unique, in which case you have a set of excess demand vectors, and under fairly general conditions, you obtain an equilibrium in this manner. It is an alternative approach to the existence problem. And I want now to return to a statement I made earlier and also Wednesday, and to justify it fully, namely, why does the existence of an economic equilibrium imply a fixed point theorem? There are two parts to the argument. The first one is an observation made by Zawa in 1962, and this observation says that the theorem I have just stated implies Kakutani's theorem. This is how you can prove it. The proof is extremely simple. Here is the set capital P, which will be the basis, which will be the space in which we operate. And Kakutani theorem says that if you take any point here, associate with it a non-empty subset, which I will call phi of P, in such a way that phi is upper semi-continuous, phi of P is convex, then there will be a P star that will belong to phi of P star. That is Kakutani theory. And I want to derive this statement from the theorem that we have just given. And this is how the proof goes. Take P like this, and now the hyperplane orthogonal to P, project on this hyperplane, so the set in question becomes here, I am not sure that my angles are right as they should be, psi of P. So we have associated with P the subset psi of P. Surely this is a convex set because this one is convex. If this correspondence is upper semi-continuous, this one is, psi of P is equal to 0, since psi of P is in the hyperplane orthogonal to P. Therefore, all the conditions of the lemma that I gave you earlier are satisfied. And there is a P star such that psi of P star intersects RL minus, which I have shaded here. And I claim that this implies that P star belongs to phi of P star, as you can perhaps see intuitively. If you have a point y in the intersection of this set and of the negative orthant, take the point x, of which y would be the projection, then you will see, I trust, that y is indeed the projection of a point that belongs to its image. So you can derive Kakutani's theorem from this lemma in an immediate way. This leaves unanswered one question. That is where the theorem on the characterization of aggregate excess demand comes in. the following question has to be answered. Here, in order to have Kakutani's theorem, it must be the case that given any phi, there is an economy that generates it. And now we know that in the particular case in which we have a function, f, so we are exactly in the situation I have discussed before, you have a given excess demand function, if it is assumed to be continuous, satisfy Valras law, we can generate it with an economy. So that completely answers the second question. You see the difficulty. If you had here a correspondence with special properties, then conceivably it would be possible to prove the existence of a P star satisfying this relation with a less deep theorem than Kakutani's theorem. But if you know that the correspondence from P to phi of P is completely general, then there is no hope. And that is precisely what the characterization of aggregate excess demand does in the case of a function. Let's see. We will go quickly over my last comments for the day, but you can slow me down by asking questions or raising objections. I have mentioned briefly on Wednesday that the existence problem could be presented geometrically this manner. If you have normalized the price vector by taking the length to be 1, then the excess demand function is a tangent vector. And if you have monotony of preferences, then surely near the boundary of the positive unit sphere, the aggregate excess demand is going to point inwards. And continuity of f of p implies then that there is at least one point on the surface of the unit sphere, that is irrespective of dimension, for which f of p vanishes. That is a fixed point theory. And it's a very appealing way to look at the situation since you have this geometric picture. And now let me try not to use the blackboard and tell you about other approaches to existence. One of them is the algorithm of Scarf and its successors. So you try to calculate an equilibrium of which the existence has been proved here. And surely if you can calculate an approximate equilibrium, then by your limit argument you will obtain an equilibrium. Well, that is another approach, a very interesting one, because, again, a comment on method. Here is an abstract approach, the concern with obtaining a model which is fully formulated, for which one knows that the central concept exists, and this has led to the algorithms of Scarf type, which are used by applied economists in a variety of fields, including public finance, economic development in particular. Another quite different approach has been proposed by Snell, who has given a differential process which converges generically to an economic equilibrium. And that is, if you think about it carefully, is an alternative way of looking at Scarf's algorithm. What Scarf does in a discrete context, Snell does in a continuous context. But the two approaches are very similar to each other. What have been the extensions of these results during the last decades? Existence has been proved certainly easily in the case where you have external effects. That is to say, For instance, your preference relation depends on the consumption vectors chosen by the others, or the production set of a consumer, of a producer, may depend on the productions chosen by other producers, etc. This can be covered because if you have looked carefully at the proof that I gave via a social system, everything there can be made to depend on the actions of the others. So utility depends on the actions of all the consumers. The set of points to which you are restricted depends on the actions of all the others, and that is one way to do it. Nascalay has proved that you could obtain existence without assuming either completeness or transitivity on the preference relation, which was quite a surprise at the time when it was obtained. Aumann has proved that convexity could be dispensed with in the case of a large set of negligible agents, and that is the measure theoretical approach, of which a counterpart is the non-standard analysis approach, which has become more popular. Non-standard analysis is not immediately accepted by mathematicians. We don't question its rigor, but believe that one can dispense with it. But I am not so sure, because it has suggested modes of reasoning, in particular Anderson's paper, of which I will give you some account next week. So we have those two alternative approaches, the measure space approach and the non-standard analysis approach, both of them dealing with a large number of economic agents. In the recent past, there has been much work done on infinite dimensional commodity spaces. That is the class of models in which you have infinitely many commodities. As you can imagine, the analytical difficulties become very great, especially when you have at the same time infinitely many agents and infinitely many commodities. But this has given an opportunity for a number of powerful mathematicians to display their mathematical abilities. And very interesting also in the recent past has been the work on non-convexity for producers. Then we know that the usual rule, maximization of profit given the price vector, is not going to work. And so what various researchers have done, and possibly the best survey that I have seen recently, was given by Bernard Cornet, C-O-R-N-E-T, not yet published, I think, and I don't have a copy here. But you have pricing rules for producers operating under non-convexity, and of course you want to be sure that with those pricing rules there will be an equilibrium anyway for the economic system. So those are the areas of recent research which have been the subject of greatest activity. I am a little skeptical, to be frank, about some of the generalizations here, but I find this type of work very interesting, because convexity of production sets is one of the bugaboos with which we have been so worried, about which we have been so worried ever since economics became formalized. And now is the time for you to ask questions about anything that I have said. Yes? No, you need convexity of the aggregate production set, capital Y. That is sufficient. which gives you a little comfort, not that much, but at least it tells you that you may have, for certain producers, increasing returns to scale, but nevertheless everything is all right if for the economy as a whole, for the world economy as a whole, you have non-increasing returns to scale, or constant returns to scale. That is the content of the mathematical result I have given you.
That implies that something could apply to the world economy, which might necessarily apply to different countries.
Well, if, of course, there are no custom duties, and if the world economy is not tampered with.
Now, demonstration that we gave of deriving from equilibrium to 6.3. Now, that depends quite critically on the orthogonality of the two vectors, which means the boundary is law. Can one think of dispensing that boundary law at all?
There is a strong form of Walras law, a weaker form. The strong form consists of saying that you have P dot f of P equals 0, and the weaker form is that P dot f of P is smaller than or equal to 0. If you have the strong form, then you can give a proof using the positive part of the unit sphere, which is very nice. You cannot do it in this case, but then you can use the excess demand approach like this, if you know that f of P, either a point or a set, is below the hyperplane, then everything is all right. This is not very damaging because eventually it rests on an assumption of insatiability of consumers. It only tells you that if you are a consumer, here is the set to which you are restricted by your budget constraint. You are going to choose a demand which is in the budget hyperplane, not below. Now, this has to be interpreted carefully, clearly. If you take commodities that are not properly dated, it does make no sense, because we know very well that in a particular time interval, a consumer may decide to save and to consume less than his income, or to dissave, to borrow in order to attend the University of Canterbury and refund later the amount of the loan. But if you take a proper concept of dated commodities, then presumably over time you are going to repay your debts and you will be on the boundary. I like to illustrate this insatiability assumption and its consequences by saying that we do not commonly observe consumers who burn dollar bills for the pleasure of burning them, which would mean exactly, which would be meant by this statement if the point were below the budget hyperplane.
So I have a question that the rationale behind assuming the strong form of understanding.
Yes.
I accept that as the assumptions you on the hyperplane and that is. But I was just thinking if a similar kind of, if the same term could be possibly true without bias. In that case, the geometry would not apply.
You mean not even this form?
Well, first of all, can we have that?
Certainly, it can be proved with this. Yes, that is this situation. That will do. Although you have here implicit an assumption of free disposal, but many of these assumptions can be greatly relaxed. I have written a paper which I don't advise you to read because it's so complex that I once thought, and that is the only paper for which I thought that, if I lose the manuscript, I will never rewrite it. And that is a paper I published in the International Economic Review. The date was approximately 63, 64. So we can greatly relax these assumptions, free disposal and irreversibility, although they do become very complex. But, and so this theorem can be phrased as follows. Here, suppose that you have simply a cone then we will normalize prices by restricting them to the intersection of the unit sphere with the cone. And you have to use the unit sphere, really, because the cone can be very large. Then let us take the polar of the cone, which would be something like this. Then for every p here in the intersection of the unit sphere with phi, we assume a phi of p that is subject to an inequality of this type, that is upper and continuously with p, and the statement is that there is a p star such that phi of p star intersects, and I will call the polar cone C0. C0 is not empty. And that is true for extremely general cones. In fact, for any cone like this, which is convex, closed, and which is not a linear manifold. That is the only case that is excluded. If C were a linear manifold, then clearly it could not be true. Let me give you an example. Suppose that C is this straight line. Then the polar is the hyperplane orthogonal to the origin, to C through the origin. And if you have, for the intersection of C with the unit sphere, which in this case would be just 2 points, if you have for this value a phi of p which is like this, below the hyperplane, for this value a phi of p which is like that, clearly it may be the case that none of them will intersect the polar cone. So for a linear manifold it will not do. But aside from that, the cone C could be closed, convex, not a linear manifold, and this result would hold. So that gives you a very general result that you can use to prove existence without free disposal, irreversibility, the like.
What problems, if any, with the methods of systems that you've given us today arise if amongst the set of commodities there are some pure public goods?
Yes, of course, that is not covered here. Then you have to use a concept like the Lindahl equilibrium, and there are existence results of that type. I have not covered them. That is one extension. So you have not covered. There are others as well. It's not an exhaustive survey. But it can be done. You have a wealth of tools, the most general being Kakutani type fixed point theorems, but there are those algorithms, the differential processes with which you can obtain existence.